Buenos días y bienvenidos a todos. Hoy me toca a mí presentar a nuestro ponente y para mí es un gran placer presentar al profesor Helmut Telle, el cual recientemente he tenido también cosas que hacer relacionadas con temas de didáctica. Y la charla va a ser en inglés, ¿vale? Creo que la presentación la voy a hacer en castellano, ya que todos los que estamos aquí somos nacionales. Helmut, su alma mater es la Universidad de Colonia, ¿verdad? Sí. Donde allí realizó su doctorado y a partir de ahí desarrolló su carrera a lo largo de distintas instituciones y universidades. Primero hizo una estancia postdoctoral en Toronto, en la Universidad de Canadá, siempre trabajando con espectroscopía láser. Posteriormente en la Universidad de París-Saclay. Y ya en el 84 ya se traslada a Swansea, donde pasa a ser profesor titular de la Universidad de Swansea. Su línea de investigación allí está basada principalmente en tres tópicos, siempre relacionados con la espectroscopía láser. Una es la espectroscopía láser remota para el estudio y el análisis de medios digamos, medios nucleares, ¿no? Medios donde es necesaria la detección remota. También el uso de espectroscopía para detectar envejecimiento de explosivos. Y ya hacia el final de su afiliación con la Universidad de Swansea, desarrolló una línea de microscopía Raman confocal en un nuevo centro de nanosalud, el cual fue cofundador del Centro de Nanosalud de la Universidad de Swansea. Desde el 2004 hasta ahora es investigador, profesor e invitado en la Universidad, en el Instituto Tecnológico de Título, donde realiza espectroscopía, colabora en proyectos con la realización de espectroscopía Raman para análisis y monitoreo de gases radiactivos. Y desde el 2018 es profesor honorario de aquí del Departamento de Química Física Aplicada y actualmente está involucrado en tres líneas. Una que tiene que ver con la espectroscopía láser de hidrocarburos, otra con la microscopía Raman en películas delgadas blindadas, creo que está en relación con lo que hace en Autónoma. Y una última, espectroscopía láser de nanopartículas en colaboración con el Instituto de Ciencia y Materiales de aquí de Madrid. Así que, bueno, esto es muy, muy interesante para nosotros. Así que te damos la bienvenida y gracias por estar aquí.
Gracias. Well, the organizers of this seminar series have asked me to torture you with an English presentation, which is good for me because it's much simpler in the preparation. So basically what I want to do today is give you a little bit of a flavor of some of the research activities I have been doing for the last few years, both externally, internally here to Madrid. When I actually started to prepare this talk, I thought, well, I give you a general overview and a lot of examples. But then I realized that graphene has actually sort of a knowledge explosion over the last few years. And if you look, whoops. Actually, if you look at the bar graph display of publications over the last few years, you see that there are thousands of publications every year only in the field of scientific research, let alone industrial applications. But by and large today, graphene research is driven by industrial means, and you can actually see here that on the timeline that until the year the Nobel Prize was awarded for graphene research, everything was, or most of the things were scientific and fundamental research. And afterwards, mostly everything ranked about industrial applications. And if you look at where graphene is today used in real life, so to speak, you find that it's used in electronics, it's used in aerospace, in defense, in energy sector, and so on and so on. And if you look at the money which is being made these days with graphene product, it goes in the multi-millions. So it's no wonder that a lot of interest is in fundamental and applied research of graphene. So basically, this whole thing then led me to realize that basically I could not give you everything, but that I had to be very selective, and in particular that I probably could not answer the question asked in the title, is it the wonder material? Because I simply can give you slight aspects and everything is open for interpretation. So I will structure my talk along this menu. I will start with a few general remarks about carbon and graphene, then move on a little bit to detection methodologies to characterize these samples, and then use 4 particular examples of analysis of samples to demonstrate the power of graphene and its applications, and the strengths of laser spectroscopy to actually analyze these. And then I finish up with a few final remarks. So let us start actually with what is carbon and what is graphene. I don't think I have to tell people here from the chemistry and physics departments what carbon actually is. It is a very, very common element, and the tremendous strength in particular in chemistry is that because of its 4 valence electrons, it can actually bond to more or less every element in the periodic table. So if you take carbon in your hands, you basically have a black lump of material, and it is a solid. And the most common form of carbon is actually graphite, which we actually know from textbooks as this hexagonal structure in layers. So then if you take one of these layers away, then you are at the material which we call graphene. And with that, we can even continue to fold it up, roll it, and we end up with carbon nanotubes. Okay, it's not as simple as these few words of description tell you, but it is actually possible. And then we have certainly the other allotropic forms like diamond, fullerenes, and many, many others. So if we actually, I shouldn't breathe too close to it. So if you look at the electronic structure, it becomes clear if you look at the possible bonding that you have, because of the possibility of arranging the valence electrons in certain configurations, that you have different ways of bonding in the end the carbon to other atoms or other materials. So it is simply the way that you have a configuration in which you have 2 p configurations and 2 so hybrids and 2 p orbitals. You have a configuration where you have sp2 hybrids and 1 p orbital, and you have then 4 sp3. So this on its own does not tell you very much, but you have to go for the situation that you bond actually these atoms together. And if you actually bond carbons in its sp configurations, for example, the lowest one, which is 2 carbon atoms, then you actually have 1 sigma bond and 2 pi bonds. So it's a triple bond, which we all know, for example, in the molecule ethylene. If you go one step up to a sp2 configuration, then you have 1 sigma and 1 pi bond, and you have a double bond, which, for example, is the simplest hydrocarbon molecule, ethane. And you go up to the final stage, the sp3, then you have a single sigma bond, and you end up with ethane. If you then go to higher structures, there are loads of hydrocarbon molecules and organic molecules, as you all know quite well, but elements where, or configurations where lots of carbons are together are in the sp2 case, the graphene we are interested in, and also those who want jewelry, it's the diamond configuration. Now, after this very brief survey of carbon, let us go actually to this larger structure of graphene. And here you have again some of its properties, how it's arranged. Basically, each carbon atoms has 3 sigma bonds to its neighbors, and a sort of delocalized dangling pi bond. And this is actually the reason why graphene is also very conductive. So it is nearly as conductive as copper. So in a certain way, this opens up the door to use this material later on, we come to that again, as a sort of a sensor which responds to an applied voltage. And if you change something with your graphene sample, then the current through the sample will actually change. So how actually do you actually make graphene? Because on the previous slide, we saw you take 1 layer of graphite, but that is easier said than done, and at least on paper. So there are 3 main techniques, there are many others as well, which are applied these days for commercial graphene samples. One is micromechanical removal. And that is actually how I produce my first graphene samples. Take a piece of graphite, a little bit of sellotape on top, pull the sellotape off, and you have graphene on the surface of the sellotape. This is possible, but for a mass market, this is not a very good solution because it's very time-consuming. You can do it only in small quantities. Then you have, in addition to that, the electrochemical preparation. And with that, it is very simple and straightforward to generate single layers of graphene. But the size of these particles is normally very small. And also, it's relatively costly to produce that, in particular, the solvents you actually need for this. And then the third most common procedure today, which is applied by the majority of companies who produce graphene, is chemical vapor deposition. And again, the advantage of this method is that you can do large-scale production and large sizes of samples, and you can do very thin layers indeed. So what are the actual uses? I pointed them out in the very beginning. And as I said, there are plenty of uses in various fields in industry, but also medicine, electronics, in the food sector, and other applications. In particular, I was amused about one, alcohol distillation. This is probably very important for the students at the weekend bench. So basically, let us now delve a little bit more into the details of graphene and why it is so superbly versatile. And here I've given, in relation to the energy level diagram I've shown in the very beginning for carbon. Here now we have assembly in molecular and solid form. And here's a picture of the band structure in for such a graphene sheet. And it's sort of a beautiful display of how things may look like in such materials produced by theoreticians. So I never could do anything like that. So my presentation of these potentials and potential surfaces is a little bit more simple, but it is sufficient to explain what we actually need later on for analysis, what sort of transitions are possible in these materials and the potentials they have available. I do not want to go into details, but they are basically sort of different main modes in the system, because basically we cannot any longer sort of talk about energy levels of individual particles or atoms, but it is embedded in a crystalline structure. So therefore, we have to talk about, in particular, phonon modes in the system. And as I said, there are three particular modes which are common to pure graphene. But they also then, if you contaminate it, and there's no way around contaminating the system, then there are further modes which are related to defects in your system. So basically, you actually will find that any of these vibrational modes in your system, they're associated transitions simply because of the energy spacing of these, and they are related to the letters I've shown on the previous slide. So basically, these will be spectra you will encounter quite a bit in the latter parts of my presentation. So now let us go to how do you actually characterize in reality samples of graphene, other than a theoretician on the back on an envelope calculating something for you and saying this is it. So you have to do it in reality. So there are a number of techniques how to analyze such samples, and there are sort of three different types. One is that you can get spatial information because you have a sheet of graphene, so it is sort of a single layer surface. So we get surface information with the technique of atomic force microscopy, of scanning electron microscopy, and so on. But that does not tell you anything about the composition of the samples. So for that, you need the elemental and chemical composition of your system. And here, two other techniques, which are common, XPS and Fourier transform infrared, give you information about the content and the chemical bonding information and so on. But you have lost the spatial information because it's sort of a general material analysis method. So here, not exclusively, but the most common method today is confocal Raman microscopy, where basically the Raman spectrum gives you information about the chemical composition. And if you move your sample underneath the microscope, you get information on the spatial distribution of these compounds, both in lateral direction, but also in depth profiling. There are many other methods as well, and they are normally used in special cases where you want some additional information. For example, what is the conductivity of the material, and then you do a conductivity or current measurement. Well, I will therefore, in my talk, basically concentrate on presentation of results from confocal Raman microscopy. Now, just to remind you, again, most people are familiar with it from their practicals in their studies at undergraduates, but probably by now have forgotten much about it. Raman, or the Raman signal, is not like in infrared, an absorption process, but it is a scattering process. So basically, the photon which you send from the laser to the sample is not absorbed, but it is scattered, and it can be scattered in three ways: either elastically, so that nothing changes in the radiation you observe, or it can be scattered inelastically, so it leaves basically the sample you probe in an excited state, but the photon which comes off the particle is a difference between the excitation wavelength energy and the internal vibrational energy. And that actually then gives you sort of a spectra, which is the very strong elastic scattering peak, and then some Raman peaks in the Stokes and anti-Stokes, meaning that you start at the ground state or you start at an excited state. And from these individual peaks, you can identify what material it is. Here's just a handful of examples that you can actually immediately determine what the material actually is. And actually, because these signals are linear, proportional to the number of particles you excite, you also can get some information about the concentration of these materials. So how do you realize such a confocal Raman system? It is basically that between your sample and your detector, you have two instruments. One is a microscope arranged in confocal configuration. That means you only get radiation from actually the sample surface, where the focus of the laser beam is. Everything else is blocked by a pinhole in the system. And the second is a spectrometer, which actually gives you a complete spectrum of all components in your system. And here's one of the systems with which I was working during my time in Swansea. Actually, these are quite expensive beasts. Mostly you are thrown back today by 250 to 300,000 euros. So that's not an easy task, in particular for us here in Spain and at the Autónoma in particular. So in order for us to have a versatile system, we actually went another way and actually assembled our own devices and actually used a setup with off-the-shelf spectroscopic components, which you assemble together, and it shows here all the individual parts. So the objective for the sample, the path through a pinhole to a fiber which goes through a detector, and also, like in an ordinary microscope, an optical path to look at an optical image. So you can compare your Raman signals to configurations in the actual sample which you see in the microscope. And as you can see, the price has come down quite a lot. And if you have already a spectrometer in your lab, then the price goes even down further. So this is why we were able to do very flexible Raman microscopy here in Madrid. And here's actually the first system we built in 2020. And there are three happy guys, myself, one student at the time from Karlsruhe, and one student here from Madrid. And we have gone into mass production because now there's a second system in Karlsruhe where we have now done the first experiments with tritiated samples. And this was one of the major reasons why we actually build our own system. Because if you work with radioactive materials, once it is contaminated, you had it. And you do not want to contaminate 250,000, 300,000 pounds. So our system, let me go back a few slides, is that in principle, with proper setup, only the objective was exposed to radioactivity. So to replace an objective, that's €100, not more. So that was one of the reasons why we built these systems ourselves, because to sacrifice a very expensive device for the sake of fundamental research is not a very good idea. So having such a system, how do we go about to actually produce the information I pointed out at the very beginning, which is spatial and spectrochemical? And the way is, like always done in spectrochemical imaging, that you have a laser which excites a sample, and then you filter out what you're interested in and detect this. But this is a method which most of you have encountered in practicals when you did Raman spectroscopy as a demonstration. But we want to have spatial resolution as well. So basically what you do is you focus your laser and then move the laser beam or move the sample. And what you get out of this is a wealth of material, of information. You acquire the data and then you store them in a so-called hyperspectral cube. And we'll see in a minute what that actually is. And then you analyze the data and compare them with the reality. So hyperspectral cube is simply a name for the complete set of information you have. It is for each position in X, Y, and it gets more complicated if you have the depth information as well. So then it is not any longer a cube, but a four-dimensional unit, which is difficult to display on paper. So basically, once you have for each of these points a spectrum, you can actually tell, for example, at a particular wavelength, what is the distribution of the intensity at this wavelength across my sample. So you pull out one of these slices, and you get here a false color image. Simply the colors here represent the intensity of the contribution at this particular point. And you can compare this with, for example, a white light image, and can then say, for example, aha, here's a cell which contained this compound. So it is a rather complex evaluation methodology, and in particular, if you have not only 1, 2, 3 spectral lines, but if you have, like in biomedicine, you have sort of thousands of compounds which contribute. And then you are faced with the problem that you have to apply principal component analysis, or like today, apply artificial intelligence for the interpretation. Good. After this lengthy introduction to what is graphene, how it can be analyzed, just a few examples. And I start off with pure graphene, so which is as clean as possible, and also devices which are made from this. And we have actually used, in general, although this is not exclusive, two types of samples. One sort of large samples, where basically the graphene layer is on top of either silicon or silicon oxide, meaning glass, or we actually use devices which are sort of arranged in type of a FET transistor. And all these samples actually are made by, or were made by, a company here in Spain, Graphene, in the Basque Country. They are actually one of the leading manufacturer of graphene samples here in Europe. So basically, let us now analyze one of these samples. And here I have actually taken one of these FET devices, which is basically made up as a transistor. We have your substrate, which is silicon, which is one of the electrodes. Then you have the insulator or the gate in an FET, which is silicon oxide. Then you have your graphene, which is the conductor, the other electrode, and you have two electrodes for which you can actually apply a voltage or current or extract a signal. So if you now scan this central part of the device, which is about 50 by 50 microns, then you get this particular picture at this particular wavelength. And it actually shows that you can distinguish the individual materials you have in the system, which is basically the graphene, which is the contact, in this case gold, and you can see the substrate, which is silicon oxide. So basically, each of these compounds has different spectra. For example, you have the graphene spectra with the three typical graphene peaks. You have silicon oxide with the typical PO phonon bands, and you have gold, which is basically only producing a little bit of fluorescence, but no particular bands. So if you actually then do this, you see exactly replicated the structure of the system. Well, let's home into this particular part down here in a little bit more detail. And here I have scanned part of the sample to actually show we can see the edge, so therefore the gold material. And you can see, let's go back, in the spectrum, you have the three major peaks. So you can tell if you make now a picture at the position of these peaks, that you have different distributions. But it shows that more or less the sample is homogeneous. So the colors you see here lie a little bit, because basically you have to take into account what actually the scale here is. So you find that the basic variation in the intensity of these peaks varies only by something like 5%. So for a sort of very delicate technique, this is quite good. In particular, if you move a sample along, even only a few microns, it is not guaranteed just their sample is actually horizontal, exactly. So if you move that, you move out or in a focus. So this also means that you have to correct, in general, for any sort of deviation of your sample from the focal point. Again, this is a method which can easily be done, but I do not want to go into details here. Nevertheless, if you look at such maps at a particular wavelength, you also can actually detect that there may be some dishomogeneities. And here's one example where we have compared actually an image generated by the method of SEM. And what you see here, SEM has a very high resolution. You see actually here, probably not from the distance, there are some black lines here in the picture. And these are actually grain boundaries of the graphene. Because in contrast to the belief of some theoretician that you can produce graphene ad infinitum, in reality, graphene only grows in small chunks, and these are then joined together, and you see these boundaries. And in addition, you see a few black spots here. These are not defects in the system, but those are actually dust grains on top of the surface. And if we can now compare this with the Raman image, evidently you can associate some of the features with the black spots, so they are exactly the same position. And you also can actually see that in the picture overlaid here, the black lines you see in the SEM image are not revealed in the Raman image, and that's simply because, as you can see from the squares, that is the spatial resolution. The resolution here is not large enough to distinguish them. So basically, there are just a few takeaways from this part of the investigation, namely that it is we can confirm that a sample is pure, that it is graphene which is not disturbed by any chemical interaction or mechanical destruction, and that you actually can see surface contaminants like dust particles. What you cannot see because of spatial resolution here in this image is actually grain boundaries, because basically in the very limit, Raman microscopy can give you a resolution of about 1 micron. But if we look back at this image here, then you have that is the dimension, 20 microns. And if you look at some of the features here, they're well below 1 micron. So Raman imaging will not be able to resolve that. So you also may need, in addition to your Raman spectroscopy, other techniques to actually fully characterize your sample. But also, we have shown in this simple study that you can distinguish between different materials. Here, very simple, graphene, gold, and silicon oxide. But it is also possible to distinguish many, many more. So that brings me to the second sample I want to discuss, and that is actually hydrogen, the graphene, which we have hydrogenated. So we have put hydrogen atoms bonding to the graphene. So the question is, why on earth do I want to bond hydrogen to graphene? Basically, much of this research has actually been driven by the idea of hydrogen storage in solid form, not in gaseous form, because people want to avoid, if you lose it as combustion, that you do not have something like in the 1930s where the Hindenburg exploded in New York. And also, basically, you find that using graphene for this type of storage is that you can bind the hydrogen to the graphene, and you have a bulk, probably not like that, and you can extract the hydrogen again by heating it up. You get hydrogen, which you can then inject into the fuel cell. once all the hydrogen is gone, you take your graphene back into the system and rehydrogenate it. So it is actually a method where you do not have a once off, but you can recycle the thing over and over again. Again, this has been demonstrated that it works, but so far only on a small scale. Nevertheless, it works. The second thing I want to demonstrate here is actually, if we go a little bit more into the detail, how to actually bind hydrogen to the graphene. So if you simply take your graphene and add a little bit of hydrogen, so you are in the gaseous atmosphere, nothing really happens. Pushing the cable now. Nothing really happens. Basically, is that you only have van der Waals bonds of hydrogen molecules on top of the graphene. And the binding energy is so small that even at room temperature, once you take the hydrogen away, everything is gone again. So you need to actually do chemisorption, so build a proper bond so that you have hydrogen atoms which bond to the system. So you go, therefore, from the unperturbed carbon in your graphene to a situation where you now have a hydrogen bonded to it. So the configuration changes from sp2 to sp3. So that is the electronic configuration. But in addition, you also find that actually if you attach the hydrogen, it pulls on your graphene, and therefore you go from the flat surface to one which is distorted. So the whole thing actually is that you will that change actually the properties of the material, and you will see that in the spectra of the Raman, but you also see it actually in conductivity of the sample. Because if you take graphene, where you have your pi bond, which is dangling, so therefore the pi electrons can move freely through the graphene. So that means it's a very good conductor. If you all of a sudden, by a bond, you take away this free moving electron, it's quite clear that there are less current flowing and there's a higher resistance of the system. So basically, you can immediately tell if you measure Raman spectra and conductivity of the sample, whether you have attached hydrogen or not. So basically, how do you do that? Because normally we know that hydrogen will exist only in molecular form if we don't do anything to it. So there are two methods how to produce the hydrogen atoms, which are necessary for the chemical bonding. One is by thermal cracking. So there are commercial devices available which enable you to more or less to and get hydrogen. So basically, you now can probe your sample once it is being exposed to hydrogen. I don't know whether this is clear enough to see from the very back, but what you can see that from the pristine situation where you have these two dominant peaks, so the system completely changes where this peak disappears and an additional peak appears. So basically, from the ratio of these two peaks, you can actually determine how much graphene has actually been, how much hydrogen has actually been absorbed on the graphene. And you can then also make maps of this and distinguish how well and equally is this distributed. And you see here a series where from very few hydrogen atoms exposure, it gets higher and higher. So more and more hydrogen is absorbed of the sample. Now here we actually did not have such a hydrogen generator available, which cost something like 20,000 euros or so. So we did sort of something which chemists in the lab tend to do. They use an electrolyte and a bath, put some electrodes into it, and let a chemical reaction happen. And exactly that is what we tried as well. You put your graphene as one electrode in the electrolyte and have another metal electrode. You run the current through it, and what you do in that way, you dissociate the H2SO4, and some hydrogen will be there in atomic form to absorb on the sample. So here is the result of our first attempt. That was in 21. And as you can see, we were not experts yet, because partially we destroyed the sample in the process because you touch it with your hands. And if you remember, graphene is a single layer system, so less than a nanometer. So clearly, if you touch it, boom, it goes. But nevertheless, we were able then to do Raman microscopy on that and have a distribution. And quite clearly, you can see the damage we introduced because there's no signal left. But you also see a difference between the top and the bottom, where the bottom was the part which was dipped into the electrolyte and the top not. However, if you know about electrolytes like that, you know that any aqueous sample has surface tension, so it creeps up your sample. So basically, what you see here, that you do not have a straight boundary, but you have a gradual transition. So here, there's more hydrogen attached than is at the top here. So basically, the takeaway from this brief study is that it is possible that you can hydrogenate graphene, but that basically the wet and simple approach is certainly not as good as the one where you do thermal cracking in the system. But nevertheless, you could produce reasonable hydrogenation of samples. With the thermal cracking, you can generate about 25% of coverage. Here you have to keep in mind that these samples are on a substrate. So you can attach actually hydrogen only to the top. So basically, if you want to use a hydrogen bond to each of the carbon, you need 3 from the top and 3 from the bottom. So we are missing the bottom. Nevertheless, 25% is quite a good percentage, whereas in our case with the wet generation, we only could get as high as something like 30%. Okay, next sample is actually, instead of hydrogen, we use tritium, the radioactive isotope of hydrogen. So you may ask, why on earth do you want to tritiate your sample? And there are actually 2 major applications for or needs for investigation of how tritium reacts with graphene. And one comes actually from industry, in particular the energy industry, in the form of future fusion reactors. And that is if you look at the system where basically the fusion is taking place between deuterium and tritium, the complete system is actually exposed to tritium. So basically that means you want to have protective layers inside your system, which actually protect your metals from erosion. And one of the ideas has been to do sort of covers of the surface with graphene, which then absorb the tritium and therefore keep it away from the lower levels. And the second one is outside the reactor, because you cannot this huge amount of tritium throw into the atmosphere. So everything is recycled. So in the recycling, you actually have in the gas now a mixture of deuterium, tritium, but also DT, which is actually the mixed isotope molecule. So you have to separate them again for the injection of pure deuterium and pure tritium. And that is actually done with isotope separation units, where nowadays membranes of graphene are used, which assist quite strongly sort of in catalysts the separation of these isotopes. So this is one application. Another application is in the scientific world, and that is our Katrina experiment in Karlsruhe, which is to measure the neutrino mass. This is another story, but also here we have lots of tritium involved, and the complete system is shown here. It's huge. It's 70 meters long, and you can see the dimension here when our spectrometer was actually delivered in the path through the village of Leopoldshafen to our institute. So it's larger than the houses around. So why do we actually want tritiated graphene? Because the experiment is still going on 24/7. And therefore, there's no chance to do any sort of testing of new things in the system. And for example, there is the ongoing research into using new detectors, which are more sensitive than the previous one. Fortunately, we have a small, it's still 10 meters long, small spectrometer, very much resembling this one, but in smaller form. And this then can be used to actually test with some tritium samples new detectors. But there are two caveats here. One is it's not connected to the tritium circulation. And the second thing is that you do not want to contaminate your complete system with a flowing gas through it. So here comes the graphene into place. You bond tritium to it, so you have it in solid form, so you can put it in, take it out, and no contamination left in the system itself. So basically, the way how we do that is the two methods I discussed previously, electrochemical or thermal generation of the hydrogenation or tritiation does not work, because one, for the electrochemical path, there are no electrolytes available, at least not in that large amount you need to do a tritiation in a bath. And the second is thermal cracking. In principle, it's possible, but in practice not, because all the commercial instrumentation is not compatible with tritium. So it has, for example, polymer O-rings, which will be attacked by tritium and so on. So the way we actually solved the problem, we actually exploited the self-radiolysis of tritium, because it's radioactive, has beta decay, and in the beta decay, it actually generates from the tritium molecule helium plus tritium, helium plus tritium ion, and the daughter molecule. So basically, in this step, we have provided tritium atoms which then, because they have a large energy, are in collisions slow down and then are able to attach to the graphene surface. The way we did do that, and because you have no way in a closed chamber like that to actually look at the system in real time, so we placed 4 of the samples into this chamber. One was contacted to actually send, as I said early on, an electric current through it, and with increased hydrogenation, the resistance increases and the current slows down. And then some other samples for comparison to do other experiments with it. So the procedure of all that is that first you you expose the sample to tritium for a given number of hours, and then before you can analyze the samples, you have to make certain that everything which is physisorbed in the system is actually taken out. And as I said before, probably you remember one of the slides, the chemical bond only is broken if you go beyond 400 degrees, but that physisorbed van der Waals bonded molecules disappear already with low temperatures. And if you go, for example, to 100 degrees, more or less you achieve that all the physisorbed tritium disappears. And once you have done that, you can do loads of experiments, and the important one is here, the Raman microscopy, and then some comparison to check that everything is the same between the contacted sample and the non-contacted sample, because again, with the contact, you actually produce mechanical stress on the system. And you also want to be able to actually test whether it can serve as a tritium sample, like in the hydrogen fuel cycle that lives for a long time. So we are now, after 1 year, we're now re-evaluating one of the samples to determine whether it still contains tritium or not. So basically, as I said, during the actual tritiation process, we were not able, like in the one experiment I have shown with hydrogen, to continuously monitor with Raman spectroscopy, because this chamber had no access for optical measurements. So we had to rely on resistance measurement. And here is actually the example. We start more or less at 0. So it's completely conducting, and then with time, more and more tritium, it's actually absorbed until it saturates, that all possible bonds are occupied, and then you have a saturated signal where you have changed from sp2 configuration to an sp3 configuration. Now, after the experiment, so at this point, we have taken the sample out and put it into our Raman microscope. And here are a few examples of the measurements of these samples after the exposure to tritium. And here is the complete picture of the 10 by 10 millimeter sample. And you see actually here in the corner, well, this corner is actually out because it was a little bit turned. You see black parts, and those are actually the points where the electrical contacts were at the sample, and basically you destroyed in the way the graphene. But at all the other parts, you see that basically they are sort of some signal you're seeing, which is relatively homogeneous, and you see a few points here which are exactly similar to the ones I've shown for the pristine graphene, which are basically dust particles which had accumulated on the sample. So if you now home in into this central part, for example, and do a scan before tritiation and after tritiation, we actually see that in the pristine sample is more or less homogeneous, whereas the tritiated sample is less so. And also here is shown the ratio between the D peak and the G peak. Remember the spectra which changed with the adsorption of the hydrogen. So in the case of the graphene before it was exposed, is that basically this ratio, the D peak is not there because it only appears when you have contaminants. But that indicates here that this ratio is by a factor of 50 or so larger. This is always a problem. I think if you look at pictures like this, also in publications, yet you always have to look at the scale. Because in presentations, people tend to use the same color scale for the full range of variation in the signal. So this is sort of perceptive, because in principle, all this would be sort of blue on this scale. So in order to get some sensible information, you sort of home in into individual parts. Okay. Now, the final bit we have actually shown here, and not only shown by us, but other people, and there are lots of theoretical investigations of this, is that basically you have two types of defects. One is that you have actually atoms or molecules absorbed onto your surface. But the other defect is, which disrupts the flow of current, is actually sort of mechanical defects, where actually your graphene layer is destroyed. There are holes in it. And also, therefore, there are less current flowing through it. So how do you distinguish between these two? Because basically, meaning that there are defects, they will actually result in similar signals in your spectrum. So again, you here exploit that there are different transitions in the bands of graphene. And if you look at the ratio between another peak, not the G peak we had for determining how much hydrogen or tritium is on the surface, or any other atom if you want, that gives you some idea about the amount of adsorbed particles. And the ratio between these two other peaks gives you an information about how much damage is in your system. So if you do that, you can actually quite nicely distinguish between different types of disruption of your current in your system, whether it is sp3 types, so meaning you have adsorption of atoms, whether it's vacancy types, where you have actually damage to the graphene layer, and so-called boundary types, where you actually are at the edges of your system. You can also tell something about that, whether there are molecules attached or not, whether it's a smooth or a ragged boundary. So basically, if you look at that information and plot the two ratios with respect to each other, you find that, for example, for one type of damage, you get a slope between these two ratios, which favors the sp3, another slope where you only have a mechanical damage. And we actually looked at our tritium samples, and there's at the moment, or when this was produced, there's only a preliminary results. We had only one data point at that moment. In the meantime, it's much more. So basically, we have seen in our tritium sample that we have a combination of adsorption damage and actual mechanical damage to the system. And this is no wonder, because tritium is radioactive, produces electrons of 16 kiloelectron volts, and they will hammer your material and destroy it in the way. Nevertheless, you can take away from this study that we were able to tritiate the samples for whatever reason, but that we also were able to distinguish between different types of defects, whether it was adsorption or chemisorption, and whether it was actually physical damage to the part. So that brings me now to the final topic in my discussion here, and that is actually using graphene devices for sensing applications. Now, the reason for that is that today graphene sensors is a wide range of applications, and there are thousands of publications over the last 5 years or so, and you find applications in chemical sensing. So you can look at adsorbed different chemicals, and because of that adsorption, your current through the sensor is different, so therefore you can measure whether you have, for example, a molecule absorbed or not. You can sense physical parameters like temperature or stress. And the biggest sort of line of application these days is in biosensors, which can be both non-invasive, so they attach to your body, or they can be inserted into your body. So basically how you produce such a sensor is basically that, as before, you have sort of an FET device. So you have the graphene area on a substrate and with electrodes through which actually a current can be flowing. And as I said, you can sense different things like gases, like organic molecules, like biological compounds, and so on. But for that, you have to prepare your sample, your sensor, that it is actually able to attach the things of interest to you. And there are different ways how to do that. You can use nanoparticles, for example, to sensitize your system. You can DNA bases, organic molecules, and so on and so on. It's limitless. So it's the art of the scientists to actually find the right acceptor for a particular application. As I said, the widest application is these days in the biomedical range, and there's a list here where sensors based on graphene devices are used today, and it's plentiful. So it's simply too much to explain everything. So I've picked a strange example from this year. And it was published in January, I think, where a sensor like that was used for the detection of cortisol in saliva. Who wants that? I don't know. But I simply wanted to show there's no limit to your fantasy. And there's a description how to do all that. You prepare your sample with sensitive acceptors, and then you can detect these compounds here. And the huge advantage of these sensors evidently is that they're small, which is one. They're also flexible, so they can, because graphene is only a monolayer, so you can attach it to your skin, for example. And they have tremendous dynamic range, so you can go from femtograms in a milliliter to something like micrograms in the milliliter. And this is something which is superior to many other sensors, which are accurate in a small range, but not over such a wide range. So with that, I come to the end. And basically, what I hope I have shown you here, that graphene is actually a worthwhile material to investigate, although we as scientists, and even more so CEOs of industrial entities, tend to overstate the benefits and how brilliant their stuff is. But nevertheless, already they have lots of applications evolved and are marketed and applied on a large scale. So basically, from my presentation, what we did actually here in Madrid and in Karlsruhe, where I work, is that, one, we can use Raman microscopy of graphene to actually show that whatever sample I have, I can actually characterize it. Number two is we were able to attach hydrogen atoms to it. We have not tried anything else yet. And third, that in principle, as I've shown in the sensor applications at the very end, that graphene can be functionalized for loads and loads of applications. So basically, I want to thank here at the end my co-workers who supported me in the actual work here in Madrid and in Karlsruhe, in particular also the director of the tritium laboratory who supported our work with loads of euros. And finally, a thank you to you that you came, that you listened, and probably did not fall asleep.
So, do you have any questions? Yeah.
Thank you very much, Helmut, for this wonderful talk. So I've noticed, for example, in the spectra that you show about the hydrogenation degree with hydrogen.
Yeah.
So you start from pristine graphene, and the first step is 13% of degree. The first step that you show is 13%. I mean, I understand that this has to do with the spatial resolution, but the question is the limit of detection out of these maps, which one?
Yeah. Well, it's this is a tremendously difficult question to answer in one or two sentences. But basically, it is that the sort of degree of hydrogenation I showed, those were snapshots out of the process of continuous hydrogenation. So in principle, you would be able to actually determine much finer steps, so much finer differences. What is also was clear in one of the
meaning of the
it's, for example, here this one here, it's basically at the moment with the approach we had is that from point to point, or the distribution over the complete thing is about 5%. But this is largely related to the fact that you measure at different points where the hydrogenation may be different because it's not always homogeneous. That's one. And the second thing is the way how we move our sample is that it is probably tilted a little bit, and we correct for this tilt. But how good that is anybody's guess. So we did then some other experiments where we stayed at one point more or less and moved the sample less than the laser spot, simply to probe a little bit away from the center. And that then is, depending on the time after the hydrogenation, where you are not exactly certain how much hydrogen or tritium is absorbed or how much damage you have done to your sample, which is a very time-consuming process to evaluate. But there we are basically to less than 0.1% in difference. Again, Raman spectroscopy will not give you, how should I say, a tremendous accuracy of how many particles were absorbed, because it's very difficult to calibrate this. It's much easier if you use actually your graphene with something absorbed as a sensor, meaning you have attached a voltage across and you measure the current. And with that, it was demonstrated that you can go to single particle. Yeah.
Helmut, I was wondering, related to the question,
Yeah.
how do you calibrate the efficiency rate? Because
Well,
I think that's
the-
that sample.
Yeah. Again, this is what actually for hydrogen we have not done, but which other groups have done. And with tritium, we have done that ourselves, is that at the end, you heat your sample up so that everything comes off. Okay, so that means you can then calculate from the amount of pressure you have, how many particles there are, and that is actually the amount of tritium which is absorbed on the sample, or hydrogen, or whatever else you have. You have to assure at the very end that you dissolve everything and can measure that with high precision. And there are for many molecules, there are procedures how to quantify them.
Thank you, Professor, for the talk. Very nice. I was wondering how long does it take for the filtration process to happen? It is a matter of hours or days or?
Well, you see here that was actually it certainly depends on how much hydrogen or tritium or whatever you offer to the system. Now, so in our case, it was something like 50 hours or 2 days. That is the tritium. No? With the hydrogen, you're able because the tritium was here supplied by radioactive decay, and even if tritium has a very short decay time, it's only a few particles which are produced every second. In the case of hydrogen, you can have high pressure and crack everything. So therefore, the spectra I showed before, they were in minutes. It depends on actually how many particles which can be chemosorbed you provide to the system. Okay. So it basically stops in the end if all possible sites are occupied.
Questions? One technical question: why you raster scan your sample, but alternatively you could also steer the beam, right? What
Yes.
is the advantage and the disadvantage of the sample?
The reason why we raster is that to use actually scanning of the laser beam, which can be done and is done by many manufacturers, is that a piezo scanning mirror system is very expensive. So that was difficult for us to include. The second is that our system is prepared and being set up at the moment to make in situ measurements. So that the filtration chamber has now a window where you can go through. But you know yourself from optics that if you go through a window at an angle, you do not know exactly which position on your sample you're hitting. So that's a relatively difficult part to do. So we actually move the sample. And that is what many manufacturers today have opted as well, is that because of the difficulties of integrating scanning devices inside the microscope is rather difficult and expensive. So they use actually a motorized movement of the sample stage. That is a simple thing.
Okay, so if there are no more questions, okay.
One question, sorry.
Yeah.
Regarding the emission of the tritium, it seems like they facilitate the breaking and formation of chemical bonding, right?
Yeah.
So it could be theoretically possible to apply this tritium adsorbed on graphene to a stream to have continuous reaction.
Yeah. Basically, you have to have something which sort of you want to chemisol is that the provided bond possibility by the graphene can actually bond with something you add. So if you have the neutral hydrogen molecule, there's no way of a free bond to actually chemisol. If you have an atom, once again, you have a free dangling bond. So if the atom passes, it can actually immediately bond. Yeah, so
Yeah, but my question is the presence of tritium atoms within the graphene seem to affect the carbon-carbon atoms in the surroundings, right? By radiative processes. So in theory, you can have, I don't know, ethane passing by and being affected by the same radiation.
that's what we mean. Now the example of the tritium is sort of a very different one from the normal chemisorption you have. Meaning that in the radiolysis, you produce a lot of different things. Meaning that you produce molecular ions, you produce atoms, you produce atomic ions, you have produced electrons. So it's a soup of different things. So in contrast to hydrogen, where you can produce sort of a pure flux of atoms, with a tritium, it's rather a mixed bag. That's why you see homogeneities in the sample. It's basically where you have a higher concentration of tritium or not. And then evidently both the atoms, the ions and the electrons have high energy. They bombard the surface and put damage to it.
Okay, so let's thank Helmut for his presentation.